So far, we have learned techniques to estimate both a VEC and VAR model. And our interpretation are based on the model estimation from software. But bear in mind that we are dealing with the time series data. The coefficients that we looked at before are just a snapshot. That's at one point of time. And due to the nature of time series, those effects will feed back in future periods. In other words, that's the concept of a distributed effect. So if we want to look at the full picture, we would like to look at the overall effect of a variable on the other variable over a long period of time. We need to introduce a new tool. It's called impulse response function. So that look at the response of variable to another variable's changes over a long period of time. That's a distributed effect from that variable. On top of that, we also would like to look at the forecasting of prediction based on those models. So one of those important objectives of time series analysis is forecasting. When we make forecasting, there's one thing we need to bear in mind is forecasting is always wrong. So we need to look at forecasting error and understand where does it come from. So that's when we need variance decomposition. Essentially, we look at the forecasting error and try to figure out which variables variation can contribute the most to the variations in prediction. Ideally, we do not want to have any variation in our forecasting error. We want it to be zero. But in reality, it's always positive, and that is there. If we can find out the source of those deviation, that will be very helpful for us to make a decision. This is why impulse response function and variance decompositions are very useful in macroeconomic analysis. So for example, we can use the tools to analyze the effect of an oil price shock on inflation and GDP growth, but at different point of time, and effect of a change in monetary policy on the economy. So we use impulse response functions to show the effect of shocks on the adjustment path of the variables. So one variable will make adjustment after there's a shock from a variable, another variable. So what is that path? Is it go up first, then slow down, or it level off really quickly? How long does it take for the effect to die away? So that's what impulse response functions can tell us. Variance decomposition, on the other hand, show the effect of shocks on the forecast error variance. As I mentioned before, we want forecast error variance to be zero. But if it's not zero, which variable's shock has the biggest impact, that will help us to make our decision. In other words, a VAR model can tell us whether series are significantly related to each other. So we look at a coefficient and the statistical significance of those coefficients, then we come to that conclusion. An impulse response analysis shows how series react dynamically to shocks. That's not a snapshot anymore. It's a full picture, or a time series analysis, put this way. A variance decomposition analysis is informative about the source of volatility. That's in terms of the forecasting error. In other words, VAR models give us coefficients. We can comment on the relationship between those variables. Then based on those coefficient estimate, we can derive impulse response function, and we can decomposite variance to answer more interesting questions. Now let's have a look at the impulse response function first. So assume that we have a univariate series, very simple one, and that's AR1 process. If there is a shock of size V in period 1, which means that's the value of Vt when t equals 1. The value of y in period 1 and the subsequent period will be, so for example, in first period, if the shock is V and we set y not to be 0 because, this first period, it doesn't really matter, the value will be V. And stepping into the second period, using the same equation, we'll find out, that the value of y2 is rho times V. Then we'll continue the calculation, we'll find out, the shocks are V, rho V, and rho square V accordingly. And this time pass of y following the shock is known as the impulse response function. I would like to draw attention to the fact that the only changes or only impact or shock to this whole system is just V in the first period. Later on, we assume nothing else happened. So holding everything else constant, including the initial value of Y now to be 0, we look at, okay, if there's one shock in period 1, what's going to happen in period 1 and the periods the following periods? It may eventually die out, but how soon will it die out? How big the impact is in each individual period? That depends on the size of the shock, and also depends on the value of rho, so the AR coefficient. And if we plot this, if we give a values, for example, here we set the value of rho to be 0.9, then we will find that, okay, the impulse response function is actually looks like this. It dies off very quickly. Of course, if you change the value of rho, change 0.9 to other value, you will have a different impulse response function. But you may notice that when we reach to the period of 30, the effect is virtually 0. Now let's consider a bivariate VR system. And we have stationary variables. For example, those are first difference variables already. And this is very simple. We are 1-1 model. If we have one standard deviation shock, usually we call it innovation in time series analysis, and that shock is to Y. So let's look at Y first. So that's the shock to be sigma Y. So that's one standard deviation of Y. By the way, it's convention to consider the shock in terms of a standard deviation instead of a 1 unit change. It's because variables may have a different units. But if all of them are reasonably normally distributed, the chance for it to deviate from the mean by 1 standard deviation is virtually the same. So you can make a direct comparison. So that is why we talk about shock in terms of standard deviations. So if the size of the shock is 1 standard deviation of Y itself, and we set the shocks in later period to be 0, so we only consider this one single shock and look at its effect in the current period and in future periods. And we set Vtx equals 0 for all t, which means we hold the shock from x constant. We also hold everything else constant, just one standard deviation shock in period 1. What's going to happen next? So in the first period, using these two equations, we can calculate the value of y1 and x1. And then we carry on with the calculation. We can calculate the value of y2 and x2 in period 2 and period 3, and so on. So the impulse response to y on y is this one, and the impulse response to y on x is this one, calculated accordingly based on the VAR 1-1 model that we have here and the assumptions that we made to hold all other factors constant. So this is the formula. These are the formulas to calculate impulse response function. Similarly, we can use the same equation and make the same assumption, then calculate the impulse response to from x on y and x. So that's the impulse response function. We can, once we know, for example, if we know the value of those coefficients, as shown on previous slides, so what is the value of those deltas, and the size of the standard deviation, assume that's 1, then we can plot or calculate the value of those impulse response functions and demonstrate what is the effect. So here, for example, that's the response of y to y, and that's based on the first equation, and that's the response of y to x. In other words, if there's one standard deviation shock in y from y, and that is the response of y over over 30 periods. So initial response is very big, then it dies off very quickly. And that's the response of y to x. If there's a shock from x, by the size of one standard deviation, initially the initial shock is large, but not as large as the one over there, which means y responds more to itself than to x, and still it's about half of the size. That's not negligible. And the same thing is true when it comes to x. So you may notice that same pattern. However, the value is 0.4 over there, but it's 2 over there. That's from x to itself. So that shows you which variable is more responsive to shocks from which variable. Okay, so that's impulse response function. Now let's go back to the example that we had before. Based on the VAR model that we estimated by using y and c, we can generate this impulse response function. This is from Stata. I will demonstrate how to obtain this set of output later in the Stata demonstration session. But now let's look at the result first. So left-hand side, those two panels, those two charts shows the response of DC to one standard deviation shock from DC and dy respectively. So quite clear. DC is more responsive to the shocks from itself. It's almost entirely from DC itself, and the shock from the response to shocks from dy is pretty small. It's very close to 0. And the right-hand side, those two charts shows the response of dy to one standard deviation shock from DC and dy respectively. Once again, it's more responsive to itself, generally speaking, because you can see the large variance over here, but the response from DC is not negligible from at least in the first couple of periods. So that's the difference between those two series. More, for example, you can say Y is more responsive to C, but C is basically response to shocks to itself from itself. Variance decomposition attributes the source of the variation in the forecast error. So we are now looking at forecast errors instead of coefficient estimates. So let's start with the univariate series again. It's a simple AR process. Yt equals rho yt minus 1 plus Yt. If that's all the information that we have, the best one step ahead forecast is Yt, to use this equation, Yt plus 1f means the forecast value of Yt in period t plus 1. That's basically it's just expected value of Yt in period of t, because that's all the information that we have to make forecasting in the future. So that's essentially rho times Yt, because the expected value of Vt will be 0. Then Yt minus 1t plus 1 minus Et Yt plus 1, that's essentially, this is the forecasting error. And the forecasting error will be Vt plus 1. That's the shock comes in period t plus 1. And then we can carry on with this type of forecasting. Then eventually have the forecasting error variance. And you may notice that the forecast error variance is 100% due to its own shock. So essentially, if you look at the forecasting errors, those are all the shocks from this AR1 process at different period of time. It's all these, and of course, you do have the role has a role to play in it. Now let's consider a bivariate example. So we use this regression model, and we have lag terms of both y and yt and xt in the equation. Then we can ignore the intercept term because they are constant. They are not going to change over time. And we make a one step ahead forecast. Then using the same strategy, we can calculate the forecast error. Fe here stands for forecast error. Then we check the variance of those forecast errors, and the first one is sigma y squared, and for x, that's sigma x squared. So once again, the forecast error variance is 100% due to its own shock in the first period. Then moving into the second period, things get more complicated. We use exactly the same formula to make forecast. Then we calculate the forecast error. Then the variance of this forecast error is a combination of the coefficients that coefficient estimates from the equation and the standard deviation or variance of y and x respectively. Similarly, we can derive the forecast error of x in pair 2, and we calculate the variance of this forecast error as well. So generally speaking, we want the forecast to be accurate in the long run, which means the average value of all the forecasts should be 0. But we do have a variation, which means for any specific period, our forecast is not going to be 100% accurate. So the key is to keep that variance as small as possible. But if it is not 0, what are the sources of those variance? Which elements here? We have a sigma 1 square, sigma y square, and sigma x square. Which part actually caused the variance to increase? So that's the question we want to answer in variance decomposition analysis. So let's put them into this table just to show to you, okay, for step 2, if we want to decompose the variance of forecast error. So we put the forecasting error for y and forecasting error of x in these 2 cells first. Then we look at, okay, which part comes from y, which part comes from x. So in this expression, we have a sigma y square here and a sigma y square here. So those are the parts that come from y itself. And the percentage explained by own shock is calculated in this way. So we just calculate, okay, if we have a variance from y itself, that's the shock from y, what is the percentage, what's the proportion of that in the whole forecasting error? So similarly, we can calculate the proportion explained by other shocks, that's from x. Using the same logic, we can calculate the percentage explained by own shock and by other shocks for x as well. So we decomposite the variance of forecasting error. This is the logic behind variance decomposition. And if we can look at the proportion, we can figure out whether the forecasting error is mainly caused by a variable's own shock or from other variables. It's mainly from other variables, which one has the biggest impact, or which one you really have to keep an eye on, because once it changes, even by just one standard deviation, it will significantly affect the forecasting error in our time series analysis. So this is the idea behind variance decompositions, which means those variables are not equally important in terms of their impact on forecasting error. I also would like to draw your attention to the last paragraph on the slide. So basically, it's that we are using a very simple example. We do not have the current terms of both yt and xt in the equation. And we don't have the autocorrelation issue in our regression model. So basically, we assume that this is a good model. We do not have current terms, and the errors from these models are stationary, and they don't have autocorrelation problem. If any one of those assumptions violated, which is not uncommon in practice, things will become much more complicated, and we do not have this very clear picture as shown on the slide. So this variance decomposition example is just an oversimplified one to elucidate the basic logic philosophy behind variance decomposition. In practice, more often than not, you will need to include contemporaneous terms in your VR model, and you may have an autocorrelation issue. In that case, more sophisticated time series techniques are available. That's beyond the scope of this course, but that's definitely something you really need to look into if you have this kind of specification in your VR models. The calculation on previous slide are reasonably tedious. And I also point out this is an overly simplified example already. So the actual calculation of variance decomposition is quite time consuming. The good news is if you leave it to software, it can be calculated in a rather efficient way. So on this slide, I just show the variance decomposition result by using the disposable income and the consumption expenditure data. So we have a DC and DY here again, and you may notice that the first one is the variance decomposition for DC, the first two left-hand side. So for DC, most of the variance, a very large proportion, near 100%, over 90%, comes from the shocks of itself, so DC. And it's the shocks from DY has very little impact on the forecasting error. So which means in future, if there's a big change, big variation in the variable itself, your forecasting is less likely to be reliable. But if there's some changes in DY, your forecasting error shouldn't change that much. And if you look at DY, the story is similar, but to a much lesser extent. Specifically, DY's forecasting error, the variance of DY's forecasting error will predominantly comes from in response to the shocks from itself. However, there are certain proportion comes from the variance or shocks from DC as well. It's not very large in comparison to the shocks from itself, but it's not negligible as shown on the slide.